basic electricity, we should say, general section, so we'll go over that later, but let me take attendance first. I'm going to run through, just so I have a rough idea where you guys are at with electrical knowledge, because one of my tasks is to take a group of 30 people, and by the end of the year, have you all very knowledgeable in electricity. And now some of you might already be, and some of you guys might go, electricity? I stay away from that stuff. It's scary. So it gives me kind of an idea of what's going on. So I would say 0 is going to be, I pretty much know nothing about electricity. 10 would be, well, I actually have a bachelor's degree in electrical engineering. We had a guy like that, oh man, a couple years ago, it was the year before me, he designed computer chips and stuff. And it was like, oh, what a boring class, electrical for him, right? But we did teach him how it works in our aircraft components. So if you know how to, let's say, wire a house and use a voltmeter, you're probably at about a 5. If you know not to get out of your car when the power line's on top of it, but that's about it, you might be at a 2. So as I call attendance, just give me a rough guess where you think you might be electrical-wise, and that'll help me kind of go, okay, here's where we're at with the class. So, David Alvarez.
3.
Micah Arndt.
3.
Gavin.
I have 3 or 4.
Zach Kuvar. 3. Lee.
3.
Brian Erdy.
3.
Martin.
3.
Isaac Finney.
5.
Nice. Pascal. Josiah Harding.
4.
Joshua Hewlett.
3.
Abednego. Charlie.
About a 4.
Jude.
5.
Austin.
3.
Parker.
3.
Leo.
5.
Harrison.
1.
Timothy Peak.
4.
Timothy Peterson. Oh. Sick. Sydney Percival.
2.
Trevor Rickard.
4.
Corbin.
5.5.
Yeah. Elijah Roloffs. Where is he? Looking for Elijah. Sick. Where's the extra gap in the chairs then?
Usually Zach took it.
Oh, oh, because I'm missing one up here. Oh, yeah.
I usually sit there, but I want to be by the tissues today.
That's great. Steven. Say what?
3.
Okay. I thought you said 8. I was like, yes. John.
4.5.
Okay. Anthony Walker.
4.
Daniel Wilson.
3.
Sam Yoder.
5 1/4.
Nathan Ziegelbar.
2.
Okay. All right, cool. That gives me a rough idea. I was asking my son, who's a freshman in high school, on the way home from a soccer game last night. I was like, so, do they teach you anything about electricity in high school anymore? And he's like, not really. As far as, physics class, kind of you get some. But I was like, oh, that's interesting. So we'll see where it goes, taking you guys deep into electricity. Yeah, so starting off, we got a little story with a bowl of peanuts. It's one of my favorites because electricity is one of my favorites. So a little story about a bowl of peanuts. So I used to, we'd say, call on people for church, for picking up kids for Awana. Parents that maybe didn't have a car to bring them to church. So we'd go call on them at their house or at the apartment or at the trailer park, and we'd talk with the people, we'd explain why we're happy to pick them up, bring them to church, teach them about God. So there was this one house where the kid lived with his, I think it was his grandma, old lady. I stopped by. The kid said she was in the other room. I thought she was using the bathroom or something, so he said, hey, have a seat. So I sit down in a chair, and man, it was taking a long time for her to come out, but there was a bowl of peanuts next to me. So I'm getting bored, and I was like, well, don't mind if I do eat a peanut here. It's still taking a while, eat another peanut, and I bet it was 5 minutes before she finally comes out without her dentures in. And I ate like half her peanuts, and by the time I was like, oh man, I'm so sorry. I ate like half your peanuts. And she said, oh, that's okay. I can only suck the chocolate off them anyway. So anyway, it has nothing to do with electricity other than that's an old one for me, one of my favorite jokes. So I like to say you learn better when you're laughing, so hopefully that gets you started. The objective of the whole class is that you will understand and have a usable knowledge of electricity in aviation. Now, if any of you were a 10, you would have an electrical engineering degree, which is like 4 years, 6 years, talking about electricity, and we've got you for 4 months, maybe, if you count all my electricity classes. So we give you a pretty good knowledge of electricity, the amount of stuff you have to have, but there will definitely be areas that we only touch on briefly and then move on. One of those, which I'll hopefully come back and review a little bit later in the class, is when you actually start naming the laws. So Ohm's law we'll all have to memorize for sure, the name Ohm in Ohm's law. But stuff like Faraday and Kirchhoff and Kirchhoff, those ones, ooh, it gets tricky. I'm going to teach you the concepts behind the laws, and we'll see about looping back to the names of them, because we're going to touch on a little bit of stuff, and we're going to get you the concepts and get you so that you understand what's going on or are comfortable with working with it and working with the math, and we'll build from there. I built most of this PowerPoint from general, but there will be times where PowerPlant book does a better job of kind of illustrating some concepts. So some of the slides come out of the PowerPlant book. When we get to airframe electricity, when we get to PowerPlant electricity, some of it is repeat, and some of it is just a deeper dive into it. But let me pass out, there's the book I was looking for. Let me pass out the syllabi, and you can send those down. I've got a couple slides coming up that basically have the syllabus for you, but in a different format, if I can phrase it that way. As those are going down, I'll give you a minute. What I was talking about was in your syllabi, if you go back to your knowledge section, there's a couple of them that I had, like Kirchhoff's law. Kirchhoff's law is current in, current out, voltage total. We're going to learn that stuff. Hopefully we'll be able to attach a name to it, but it's more important to understand the theory than the name. Faraday's law, same thing. Faraday's law are going to be the hand rules we teach you. We're going to start with those today. And Lenz's law we'll talk about with back EMF. So we're going to be throwing out a lot of terms in here, today especially. And as we go through over the next month, you'll start absorbing those terms. Might be a good idea if you see the yellow and red ones highlighted on the PowerPoints to jot it down, or at least take a mental note and say, okay, that's a term I'm probably going to need to know, and pick it up as we go. Today's overview, and then I'll get back into the schedule, is we're going to talk about atomic structure and electricity, we're going to talk about static electricity, and we're going to talk about magnetism. All three of those interact with each other, so I'm going to give you the basic framework of what electricity is and the basic building blocks of how we're going to make it. We're not really doing any math today with electricity because we need to get you some framework to work off. And once we get the framework, tomorrow is going to be the big, what you would think of, oh good, electricity is starting. So today is going to be just kind of an intro to get us thinking. I was driving here and I was thinking it's kind of like if we were going to say we got a class on sailing. And there's so much with sailing that has to do with the air, right? But you can't see the air around you. So if you don't know about air and pressures, we got to teach you about that before we get too deep into sailing. So that's what we're doing today, is we're teaching you kind of the physics that have to do with intro to electricity. But as we work our way through our schedule, tomorrow will be the math, and we're going to introduce the terms that have to do with the math. Thursday is actually, it sounds funny, but it's a break from physics. Dean will teach you guys how to solder, and he'll pass out the multimeter kits, and you can start on that practice for that one. It's just to give your brains a little bit of a break from listening to me. And Friday, we'll talk about some simple components like switches, and switch into a little bit of batteries, because we're not going to do a whole lot with batteries on today and tomorrow, other than tell you that there's a voltage in a battery. So this week is a pretty simple week just to get us up to speed. Once we get into next week, we'll deal deeper with our math, with our Ohm's law, so volts, ohms, amps, stuff like that. We'll actually start teaching you how batteries and generators work. Tuesday, we'll transition into AC versus DC power, teach you what all that means and how it deals within our aircraft. And then we get into components. So we'll have a day for capacitors, a day for inductors, day for impedance in doing math. You'll get a midterm that Monday, September 30, and some lab time. I'm going to go over the lab schedule in a minute. Then we get back to some more, I'm going to use the word components, diodes and transistors, and or NOR gates is building on the transistors, and it's basically what your computer is made out of. So we'll go into that, and the reason for that is, well, so much of our aviation dashboard nowadays is digital, right? And the FAA wants you to know roughly how that stuff's working, but we don't have time to give you a computer engineering degree. So we get just barely scratching the surface on how computers work. And then we kind of say, if you want to go deeper, go get a computer engineering degree. But we'll scratch the surface on how computers work. Then towards the end, what we do is we take a deeper dive. Now that we understand how the components in electrical systems work, we dive deeper into batteries specific to aviation. Deeper dive into how the generators and DC motors work in aviation. Deeper dive into alternators and inverters. Deeper dive into the actual wiring. So what's interesting there is the wiring, the most basic component, is way on the end. The reason I stuck it way out there was what you need to know at a aviation mechanic level about wiring. If I taught you up front, you wouldn't have the basics to know why. So we stuck it at the end, and we'll go back to it and learn it at a deeper dive. We'll learn about some troubleshooting and practicing, and then review for final and a final exam. So, as you can see, we're going to kind of take pieces, and the way I would phrase it is some people, when they eat their food, they eat a little bit of this, and a little bit of that, and a little bit of this. I tend to eat all my French fries, and then all my ice cream, and then all my hamburger, unless I get distracted and I'm talking too much. So we're going to do it that way. We're going to take each topic and take it one at a time. We'll review, it'll get mixed in, but that's the overall schedule. So as you're following along, you kind of have an idea of what's going on. As far as labs go, I have a suggested lab completion time. I don't normally pass these out. I normally have you snap a photo of the screen for this one, but they're all out of order. So there might be some extras that show up at the end if I get them back. Well, there'll be 2 extras for sure here. So as you pass that out, I'm going to give it a minute so you can all see what's going on. one side of your sheet has the labs listed, and on there I called it estimated hours to complete each lab, and I tried to make that working at a nice, slow, steady pace without rushing. That's how many hours you're gonna use to complete the labs. You'll notice the vast majority of them are 1 hour, they're Moodle labs, they don't take that long. And what we're gonna end up with is towards the beginning of class, as I lecture, you're gonna have a lot of lecture time with a little bit of lab time at the end. Towards the end, we'll have more lab time, but the reality is this particular electric class, unfortunately, is more lecture than lab by a little bit. As we get into electricity airframe, electricity power plant, it starts shifting a little bit because now we've got enough knowledge and tools to where we can actually do more in the lab. But a lot of these labs are Moodle labs, so they're not tools, hands and tools lab. But jumping out, lab 15, if you look at it, is completing your multimeter build. And if you remember, I introduced that one this Thursday. I've got it down as 6 hours. It's probably in that neighborhood. You're not gonna sit down for 6 hours in a row and build that thing. What'll happen is you might get 2 hours to do it this Thursday. Don't rush it. And then as we go through, let's call it this Monday. To complete 7 and 7A, I've got 1 hour, 2 hours listed. But let's say you get done with them in an hour and a half, and we happen to have 2 hours of lab time that day. You've got a half hour, you got 45 minutes, you got an hour to go back and work on lab 15, work on that multimeter. So what I don't want you guys to do is get the multimeter lab Thursday and then feel like, oh man, I gotta hurry up and get this thing done and be working on it after class, because it'll be fun. You might be tempted to do that because it's a fun project. But if you do that, as we get out into these weeks, when you get done with the assigned lab early, and you're gonna be going, now what do I do? So that lab at 6 hours, it's built in to have a little bit more time in there. If you open Moodle, you will notice that most of the labs you don't see yet. Well, you see them, you can't access them, right? I am not giving you out all your labs ahead of time. I'm slowly handing them out pretty much according to this schedule. When we get towards the end, I might start giving them to you earlier, like on this Monday, so that you can start working ahead a little bit. But the reality is, you will slowly get the labs according to basically this schedule, and you can work on them that way. That's a big reason I gave each of you one of these. I would, if I was you, hold on to this, and as you finish the lab, check it off. If you notice on the schedule, I'll get to that in a minute, if you notice on the schedule, hey, I was supposed to be done with these labs, but I'm not yet, that should be your clue to, oh, I better catch back up because you don't want to fall too far behind. Yes, question from the corner.
Not seen the course up yet on Google.
The course isn't even up.
Not rolling or something.
Go to your courses and go to all courses.
All right, let me grab a notepad. That'll be a Nick thing. He probably didn't enroll y'all. I'll be right back.
Guess we don't start electricity tonight.
All right, the good news is you don't need it yet because you only have one lab today, and we're not going to do that for a couple hours. So today's mostly lecture, but not enrolled. I don't have administrative authority to put you in, so I'm not sure what happened there. All right, so when it comes up, what you'll notice on Moodle is even if you saw it, well, you get your syllabus and stuff, But, you can't open the labs yet. I lock them out, kinda like your exam. You know how you saw your exam, but you couldn't open it? That's what most of the labs are gonna be. There are, I have it on my sheet, I think 4, 1, 2, 3, 4, that I have to physically hand you that are the paper copies that you'll turn back in as well, and I'll hand those out as they come as well. I think the first one of those isn't until next Friday, with the exception of the multimeter. So, that's the schedule, that's the idea, is we're gonna work through it all at the same pace. But be aware, if you start falling behind, you got more coming. But if you need a guess at how long each one's gonna take, you have that sheet. You'll also notice they don't go in order, right? So when you're looking at your schedule, we go from lab 1 to 3, we skipped 2, because lab 2 shows up the day of the midterm, but it's 1, 3, 4, 15, 6, 5, 11, so they're all out of order. That's so we can kind of teach you the way we need to go. Alright, other than getting in Moodle, the concept of slowly turn them out and your sheet making sense, everybody following with me? Okay, you should have plenty of time. I have 36 hours listed on estimated lab time here. This is a 23-day class, so if it was 50-50, that gives you 46 hours of total lab time, is about what we're targeting. So there's almost 10 hours of, oh, do I got extra to study, to do one twice, to ask questions. So should not be a rush on these, because we want you to get the concepts and get them well instead of overwhelm you with it. This slide should be review for you, and this is what your lab today is basically gonna be. I think Christina went over this in math class, so we're just gonna apply it to electricity. We deal with 1,000 or 1,000th a lot in electricity. So the big ones we're gonna use the most, you could say is kilo. So a kilo is 1,000. You got 3 zeros, you can say 10 to the third. Kilo is a K. So if I have 1 volt, and then I go, okay, what if I have 1,000 volts? I can say I have 1 kilovolt, right? So the big ones we use are kilo, so I'm gonna star it in electricity. And then we tend to go the other direction. So we're gonna go to 1,000th, a milli, it's a lowercase m. So that's one we use all the time, millivolt, milliamp, millihenry, so another 1,000th. And then the other one that shows up quite a bit is micro. Micro is a millionth. It's basically 1,000th of 1,000th, right? So if a milli is 10 to the negative 3, so you move the decimal place right 3, a micro is 10 to the negative 6th. You move the decimal place 3 more. And we're gonna do that math kind of in a minute just for moving. But letters, kilos, just a lowercase k, unless they write it wrong in the book or somewhere. And sometimes they'll throw a capital K at you just to try to mess you up. If you notice, we don't have a capital K. So I think that's why they can get around with that one. But the M's are pretty important. If you have a capital M, it's bigger M. We don't use that one much. It's mega, goes up to 1,000,000, but it is there. But we don't use it much, so I'm not even gonna circle it. The point is, normally we're going smaller. So a small m, just standard, is back to a milli. Small m, 1,000th milli, and easy to understand. Micro, it's a Greek symbol? I don't know how to phrase that. You take a small m and you squish it even more. So really it looks kinda like that. So they kind of took a small m and squished it down even more. That's how I try to remember it. So micro, and when you have a microscope, you're looking at really, really tiny things. So you will have to memorize milli and micro and the symbols that go with them. The biggie is small m's milli, even smaller m that you can barely read on your voltmeter unless your eyes are good, because trying to separate that part of the line right there is pretty much hard to do. So milli, micro, those are the big ones that you're gonna have to memorize and remember. Usually people get kilo easier for a kilogram. Switch the screen up a little bit and just go into a different view of it. So 10 to the third, we're adding 3 zeros, kilo with a K. If I go negative, -3 milli with a M, -6 micro with the, basically the squished down M. Occasionally you'll get some of these other, like a picofarad. Those I don't necessarily have you memorize because, well, just know it's tiny and we'll deal with it later. But the 3 to memorize are kilo, milli, micro. I'm gonna draw a number up on the board and we'll play some little math games. Let's see here. 1, 2, 3, we'll make it silly in order. 5, 6, 7, 8, 2, 1. All right, so let's put a decimal, 0. Let's put a decimal here, and I'll draw a name out of the jar, just for the fun of it, and say Parker Miller. What, roughly what number is that? You don't have to read the whole thing, but.
1,234, 5,678,000.
That's just a period. That's just a period. That's not a comma. So, if you would have stopped where you were, it's 1,234 and some change on the backside, right? So I'm going to call it a volt just because we're in electricity class. And we'll deal with what volts actually are later. But so that would be 1,234 volts, you know, and some change. All right. So if I wanted to say how many kilovolts is that? For a kilo, it's 1,000 volts. So we're going to just move the decimal over 3 spots. 1, 2, 3. So that's how we do it. So how many kilovolts? You know what? I'm going to leave my original in there so we know. Volts, if the period is there. So how many kilovolts would that be, Joshua Hewlett?
1.234.
Yeah, 1 point and some change kilovolts, right? So we move the decimal 3 spots that way to get kilovolt. Okay, simple math. I'm assuming y'all did this with Christina and it's good, but it's good to review. I like to draw and just move decimals around because it's easy. Micah, if we wanted to say millivolts, how many millivolts is 1,234 volts?
1,234,567.
Let's see, so 1, 2, 3 for milli. Now if we had to put commas in, comma, yeah, so it'd be 1,234,000. Well, I even said the number wrong, but yeah, this would be where our 0 goes. So yes, 1 million, and the numbers, millivolts. All right, and micro would be we'd have to go 3 more places and read the number from there. Those would turn into commas, and it'd be like 1 billion microvolts. So let me change this around a minute and say, let's say I have 1.2. Now what we always want to do is understand that there's a bunch of zeros or decimals. Maybe it's 2, 3, 4 or whatever. after it, right? We just don't read them after the decimal because we're like, you know what, it gets less significant. So we tend to not read them. So if I have 1.2, we'll say lowercase m, so that's a millivolt. And I say I want to convert that back to volts. I've got to move it 3 decimal places. So if I have 1.2 millivolts, and I want to know what the volts are, I've got to move it 3. So 1, 2, 3, period goes there. I can erase that if I want. Sorry, I had one, what'd I say I had?
1.2
Millivolts, you're right, I'm sorry. There's also zeros out here. If I have 1.2, let me erase this. You guys are sharp, just testing you. If I have 1.2 millivolts, and I want to know how many volts that is, yeah, sorry, so 1, 2, 3, the decimal would go there. So I would have 0.0012 volts now. So, if you're having a hard time, as we go through milli, micro, killa, you can always just draw it out, but the easiest way to do it is just bounce your decimal around and then reread your number to see where you're at. That's what most of your lab is going to be today, is just going back and forth between milli, micro, and kilovolts. I would suggest, while you're doing the homework, just go ahead and grab this out of your book or off the internet and have it sitting next to you, and it'll remind you when you get that far. So that should have been all review from Christina's class, right? Basically? Good. Alright, what we're going to do is we're going to take a 5-minute break because I got to get a little bit of a demonstration set up for this one, and then we'll come back and we'll start into chemistry. Before we take our 5-minute break, how many of you guys are familiar with and really like chemistry? Ooh, so like 3, yeah. That's about where I was too. So the reason we're going to do some chemistry is it has to do with how our atoms are built, and electricity is all about the electrons that are on the outside of our atoms. So you're not going to have to memorize your periodic table of elements like you do in chemistry, but we're going to talk about chemistry to give you an understanding of what's going on with our electrons spinning around the outside. Back to, it's just a framework to get you in the neighborhood of why electricity works and what it does. So come on back at 22 and we'll talk a little chemistry, just to give you a flavor of what's going on. I'm going to double check. 7:40. What did I say? I said what?
7:32.
Oh, 7:40. 5 minutes. Take a 5-minute break. Don't think Nick shows up till 8. Double check. see these?
Yeah.
Okay. I think it'll work then. We've got a couple different visual representations to.
I mean, I probably won't be able to see them when like people start sitting down, but.
Yeah. Alright, we'll see what happens. We'll do it a couple times and people can't see. Talking about the speed of electricity. Say what?
Whatever those are,
Holland? Hollow, no, those are micrometers, they're very expensive. Yeah, I basically just needed blocks. So.
The speed of electricity is the same as the speed of photons?
Gets complicated, it gets complicated. We don't even touch on photons much, just because, oh, how deep. Yeah.
It's a deep rabbit hole, right?
It is. I mean, we deal with electrons, which, I got my head all like tuned in to my lecture, so now I'm going back to, let's see, okay, if I go to photons.
I mean, like, is it the same as the speed of photons? You think it's like the same as the speed of light?
Right, so a photon is not necessarily an electron going anywhere, right? It's a,
Yeah.
they're things, cause they, it's either a wave or it's a particle, and it depends on how you observe it, and that's why we're not gonna pick it. It was really interesting as I was getting ready for this, actually, because they act like both, some of the visual representations that I tried to draw it, is they draw like a wave. And they call that wave packet a photon, and it was just like, oh.
Some really smart people
Yeah,
figure all that stuff out.
well, part of the issue is the way we've taught some concepts in electricity and stuff, what they're, we should say realizing what on the deeper level. That's how we explain it. It turns out, it's not actually what it is. You can still use it to do the math. So,
Like, the smarter you go, basically, the understanding of physics.
starts changing, yeah. All right. We are back. So for me, I had what they call core math in high school. It was for the kids that didn't want to take hard math. Not math, excuse me. Core science. It was for the kids that didn't want to take a whole year of chemistry. So my chemistry level is really, really basic. I was introduced to the periodic table of elements, and we tried to do some math with stuff like compounds and whatnot, which we're going to teach you about. But it was, you know, I'm not a chemist, but I know enough to be dangerous. I get to talk about chemistry with you guys for 20, 30 minutes in what I was taught in high school in like 2 months. So we're going to touch on it enough so you have an idea of what's going on. If you want to dive deeper, you can read sections of your book about it. You can watch YouTube videos. There's not a whole lot of tests on Prepware or Verbal about this, with the exception of they just want you to understand a little bit of why different materials are going to behave different electrically. So we got to get you to understand what's actually different about a material so that you understand why they behave different electrically. So most of this you could say is entertainment, not really, but you sit back, you kind of go, oh, okay, I see why aluminum conducts electricity and rubber doesn't. That's pretty much the goal of the next 20, 30 minutes is why do copper and aluminum conduct electricity well and rubber and glass and ceramic not conduct electricity well. So boil it all down, that's pretty much what you got to learn. But if you follow me and can track more, you'll have a better better understanding of what's going on. So here is our periodic table of elements that we're gonna talk about, atoms and such, in. I believe Christina talked to you a little bit about, atoms and atomic structure and matter. Matter is anything that has a mass and takes up space, right? They've got a picture over here that, turns out is not a really great picture. So we'll draw a couple, but in every atom, which is what matter, what stuff is made out of, you've got a nucleus, so you've got the center of it, and then you've got electrons that are on the outside that are zipping around. And you can get really deep into, are they really like going like this, or are they, and the reality is they're kind of going everywhere, but they tend to be a certain distance from that nucleus. When we go to the periodic table of elements, basically the difference between all our elements is how many protons and neutrons, so there's weight to each of those. There's weight to a proton, there's weight to a neutron. There's really not much weight to an electron. Just lost my marker. Zipping around the outside. So on our periodic table of elements, the smallest ones, the one that only has basically one proton in the center, is hydrogen. The number in the top left of hydrogen is 1. So it's basically got that atomic weight or atomic mass of 1. Now they give you a little bit for your electron that's zipping around the outside, and you realize compared to 1, the electron, well, there's not much there, right? So hydrogen is basically 1 proton with 1 electron zipping around the outside. We like to assign electrically a charge to the protons as, that was an X because I'm sideways, as being positive, so we call that positively charged. And the electrons we assign a negative. We say they're negatively charged. So when you see them drawn, if you see the electron zipping around the outside, we'll say, okay, the electron has a negative charge, the proton has a positive charge. Now, all of our materials, all of our elements, they want to be balanced. They want to have the same number of electrons zipping around the outside as they have protons in the middle. There are also neutrons in the middle, which they didn't draw in these. And the reality is, if I've got 1, 2, 3, 4, 5, let's see, let me count again. 1, 2, 3, 4, 5, 6, 7, 8. If I have 8 electrons zipping around that, if I was going to correct this drawing, I'd actually want to have 8. 1, 2, 3, 4, 5, 6. We'll count that one. 7. I'd want to have 8 protons in the middle as well, because we want to be balanced, the same number of pluses and negatives. Otherwise, it would have an electrical charge, and naturally things don't want to have electrical charges. They want to be balanced. So that means that the heavier or the more mass per atom an object gets, the more electrons are going to be zipping around the outside of it. Because to balance the pluses, you've got to have the negatives zipping around the outside. So we have a proton in the center. A neutron is in the center as well, and you typically will have, for every proton, as you build bigger and bigger, you'll add a neutron. So, was it? Hydrogen starts with 1 proton, and you get over to, is it helium? Helium has 1 proton, 1 neutron, and then we move over. But so you're going to also be balanced in the center with protons and neutrons in our atom. So proton, neutron, and electron. Those are the 3 basic building blocks of atoms. We're not going to go deeper than that. We're not going to talk about photons and quarks and goofy stuff like that. In electricity, that's all the deeper we're going to go. So an atom is the most basic building block of matter, the most basic building block of stuff. An element is a grouping of the same atoms. So let's say I have one atom of copper, let's say. I got one copper atom. Theoretically, I guess, that's still the element copper, but if I put a whole pile of copper atoms together, which you'd have to be able to see it anyway, element just means it's a whole pile of the same kind of atoms all on top of each other, a grouping of the same atoms. If we go to a compound is more than one atom tied together. So water is H2O. There's two hydrogen atoms and one oxygen atom. So water is a compound. If we have a lot of water, we've got a lot of these one oxygens with two hydrogens connected to it. And they're all piled up next to each other. And that's typically what we're going to say when we're at a compound, is it's multiple different kinds of atoms, but when they're connected to each other, they got a link, they're connected tightly. A molecule is the smallest a compound can be broken down. So for instance, if water is one hydrogen connected to two, I'm just going to draw it this way, oxygen atoms, that's one molecule of water. I could draw that times 1,000,000, connect them all together, and you would have yourself a cup of water, right? But when we say we want one molecule of water, it's the smallest we can break down water before it's not water anymore and it goes back into its individual elements. And matter's just anything that has weight and takes up space. Anything that has mass, I should say, and takes up space. So hopefully this was review from your physics class as well. But we had to go back to proton, neutron, electron. In electricity, we're going to be looking really close at our electrons. Each, you could say element, but usually what we're dealing with is actually compounds. So the material that stuff is made out of in the world that we're going to make airplanes out of, sometimes they're elements, often they're compounds, right? Even the copper we use, it might be an alloy of copper. The aluminum we use is an alloy of aluminum, which means, well, it's probably not pure aluminum. They probably have some other stuff mixed in with it. But each compound is going to want to have its happy place, where it's got the same number of electrons as the protons that make it up. It wants to be what they would call neutrally charged. So, for a little demonstration, I'm going to need, let's see, how many cups is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to need 10 students to come up and help me with this one. I think it's going to work. So come on up. Yeah, come on up, Brian. 1. You'll each get a cup. And then we're just going to have you line up across the front of the class here. Ooh, ooh. Okay. So you guys are all going to be my individual. You could either say atoms, or you could say, why don't you go down to the far side? One more. You got an empty cup. All right. Whether you wanted to call them individual atoms or individual molecules, probably molecules is the best word. Now, right now, we're going to say their cups are kind of like a proton. Now, the reality is it could be 10 protons, and they want 10 electrons, but we're going to make this a little simpler, and we're going to say that they're just hydrogen, or you could multiply each whole by 10 and sucker by 10. So, we're going to make you happy electrically, 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 happy electrically. Did I miss you? You're good. Happy electrically. All right, so you're happy. Now, if I were to take yours out, and for demonstration purposes, to show that you're unhappy when it's out, tip it down at the class, and we'll point it at them so we see. And the reason I'm trying to do that is that's a hole. So we're gonna get into this later, but they'll call that a hole. He's not happy electrically. He wants to have his electron back, right? So if I pull his electron out, he's not happy and he wants his electron back. Now, if all I did was take his electron out from this end, well, probably not much is gonna happen because we don't have any electrons left anywhere else. But if I take his electron, and this takes some work to drag it all the way down here, and if I give it to Micah, well, we got a problem in Micah's cup now, right? Micah's got too many electrons. He's not happy because he wants to have the same number. So what's Micah gonna do? Oh.
Gonna share.
Exactly, and all of a sudden, I have electrical current. I've got electrical current flowing. Now this is one way to look at it, is that the electrons are traveling down our conductor, and it's going this way. Now you can look at electrical current a couple different ways. What we just did was what is truly happening. We call it electron theory. Hey Nick. Nobody's actually in my class today, it sounds like, on Moodle. Would you be so kind as to enroll them? Alright, so that is electron theory. That's what's actually happening. But when we were first learning, alright, we're all happy again. When we were first learning about electricity, the early guys, they didn't realize that we had electrons happening. And they labeled a positive charge missing the electron. And I could have, maybe I should have put pluses in the bottom of each cup. So in your mind, when you see that whole thing, that's actually what they would call a positive charge, right? So what happens in the old version of how they would do it, and it's going to be how we talk about it all year, is instead of passing the electrons down, he's pretty unhappy. It took work. I had to take his electron away. So he looks at his neighbor and he says, "Ooh, I'll take yours." And now his neighbor's is empty, so show us your empty cup first. Oh, and now you're unhappy, so why don't you take his? Oh, now he's unhappy, and he says, "Oh, I'll take yours." Now he's unhappy. So, what's happening to our hole? Our hole is moving that way, right? So it all depends on how you look at electricity. Do you want to look at the electrons themselves that are flowing through the conductor? Or do you want to look at the hole where it needs another electron that's moving the opposite direction? When we do the math, it all works out the same way. You just got to make sure in your head, hey, am I looking at the hole, which is a positive charge, which is pretty much how everything electrically is drawn until you get deeper? Or am I looking at the electron, which is the negative charge? So the hole we call conventional, because that's what they started with, conventional, and electron theory, when we're looking at the electron, is the other. So, who's missing? You're missing down there. So I'm going to make you guys all happy again one more time. Everybody's happy. So because we start with conventional, I'm going to do it one more time. I'm pulling this out. Now if all I did, he doesn't want to give up his electron, Yoder, because he doesn't have any pressure from this side saying, hey, I got an extra for you. So until I essentially bring this one down here and say, hey, I got an extra down here, nobody's going to release. But once we bring it down to this side, basically that release process starts, so this guy gets the extra. So that's my illustration number one, because we can't really see electricity. So thank you guys. You can have a seat. I'll take all the suckers back. Unfortunately, I don't get to keep them today. On review day, I'm going to need a bigger cup, aren't I? On our review day for the exam, I tend to throw candy at people, so that's what it's sitting around for. Cool. So that's the simplest way I can think of to say electron and electron flow. I'm going to show you one more version with our micrometers up here. say, how fast does that actually happen? So each one of these stacks is going to represent, whether you want to call it one atom or one molecule, they've got the correct amount of protons and electrons, so they're a happy match. Now, if I were to do some work and pull one and try to put it over here, that takes some work, they're all going to want to shift, right? So there's this weird question on the speed of electricity where you say, do I look at one electron, or you could say one hole moving, because if you're conventional, it's actually the hole that moves down, and you can see the hole moving. Or do you say, how fast does that electrical force get sensed on the other end of the conductor? This is where some people get a little confused, because all that's going to happen is I added one electron to this side, and they all basically shift. So even though you could say, if you wanted to try to say a speed and say how fast is this one moving, you'd say, well, I mean, there's a certain speed from here to here, right? But it was immediately felt at this end of the conductor. So I'm going to do that one more time. So if we just move one electron in this conductor here, it happens simultaneously, basically. So the speed of electricity, they basically end up calculating it at the speed of light, because each one of these electrons are spinning around our atoms at essentially the speed of light. So if I bump one more in this atom, the chain reaction bumps so fast that it travels through our conductor or our wire essentially at the speed of light. And that's why when we're talking about electricity and the speed and how come I can send an electrical signal around the world so fast, is it's not, and I'm going to use the blue one in a minute, it's not that we're taking this guy and sending it all the way through the wire to the other side of the world. What we're doing is we're just taking essentially an electron, we're bumping it one atom over, but on the other side of the world they go, ooh, I felt that. So hopefully between the cup one of seeing how it moves and our micrometer one of, oh, I only have to move essentially one atom, but it happens to all the neighbors down the line, you get the idea of, okay, I can see why it's moving at the speed of light. And as we get into AC and DC, we'll start talking about how they move back and forth as well. So DC current, direct current, the electrons are going to keep going one way through our conductor. When we switch to AC current, they're moving one way and then reverse and go the other way, but they're all connected in that chain. So even in AC current, we can send it really, really long distances because they're all essentially connected in the chain. And you'd say electricity travels at the speed of light, so pretty crazy stuff. All right, everybody pretty much tracking with me so far? All right, good.
Conventional and electron theory, same stuff's happening, just the way you view it, right?
Yup, conventional is we watch the whole move. So we're watching the positive charge, the positively charged molecule, I guess you'd say. We're watching the positives move. In electron theory, we're watching the negative move. So they look like they're going different directions, but all the math is the same. It's kind of like taking a picture and flipping it into, what do they call that? Negative, reverse. So everything's happening essentially the same until we get into a lot deeper, which we'll talk about later. Leo.
So you're saying it takes a lot of effort to move. How does it move from one end to the other end then?
We'll get to that. Yeah. Yep. We will get to that. It can either do that chemically or mechanically with magnetism, and that's what we're getting to. But basically, we're moving electrons, and depending on if you call it the electron that's moving or the hole is conventional, and we got to make sure we understand both of those. All right. Valence, I think I'm saying that right, valence electrons. So, I have a video coming up later, but at each of our individual atoms or elements, this is a hydrogen. It's only got one proton, one positive in the middle, and one electron on the outside. As we get more, I gotta be careful because my physics teacher wouldn't like me. Technically, we shouldn't say weight because that has to do with gravity, right? Usually I should use the word mass. So if you hear me say weight instead of mass, you'll have to forgive me. I'm not a physicist. But weight is how I think of stuff. Well, anyway, so mass, weight, I use interchangeably, even though, according to my physics teacher, that's wrong. But as we get bigger, more mass, more weight, we're adding electrons. There's an interesting rule with electrons that the first, what they call shell, or the most inner circle that these electrons are buzzing around, our nucleus. There will only ever be, there's a couple things that break the rules, but 90 whatever percent of the time, there's only ever going to be 2 electrons in that inner shell. If we get a bigger atom that needs 3 electrons in it, the next electron, the third one, it's not going to be in that inner shell. It'll say, oh, I don't have enough space there. I'm going to move out to the outer shell. And space isn't the right word because it's got a really complicated thing to do with energy levels. But basically the first shell can only have up to 2 electrons. The next shell can have up to 8 electrons. The next shell can have up to 18. The next shell can have up to 32. So if we go to our periodic table of elements, if I were to just pick out titanium, it's hard to read these, but titanium has 22, has a weight of 22, make sure I got that right, sorry. I can't read it. It's got 22 protons. That is a bad picture. You know what page that is in your book? Just so I give you the right numbers.
12-3.
12.3.
22.
The number's 22, and I believe that's the number of protons, because back to my physics chemistry class, there's a number towards the bottom of the chart in there. Yeah, 22. So it's 22 protons. If you notice the weight, the mass down here, it's 40 something. So it's going to count the protons and the neutrons. We really don't care so much about neutrons with electricity, so we just kind of forget them, which is why I had to go back to my book. I'm like, neutrons, who cares? With the exception of, for every proton, we know we have to have a neutron. So titanium is going to have 22 protons, so that means if we were to draw a titanium atom, there's going to be 22 protons in the middle. That means in the first shell there's going to be 2, so I got 20 left. In the next shell there's going to be 8, so I got 12 left. So in the third shell I'll have 12 electrons. That's kind of how they build out. There's, I don't know if you say laws or rules that govern it, or you just say that's how it works. So what happens is if each shell has the number that's in there, it doesn't really want to let go of any, and it doesn't really want to absorb any. So if I've got an element that is happy, it doesn't want to share its electrons well. The electrons that are in that most outer shell, now for hydrogen, well, there's only one electron, right? So when we say outer shell, the outer shell for hydrogen is, well, it's just the first one close to it. So it has one electron in its outer shell. So for hydrogen, the valence electrons, well, it's only one. There's one valence electron. It's the one in the outer shell. If we move to, we'll just pick, I'll do this one, lithium. I think that's lithium. Is that lithium? Yep. Lithium has 3 electrons. So in lithium, we're going to have 2 in the inner shell, and then it's going to have 1 electron in the next shell out. So the valence electrons for lithium are the ones that are in the outer shell for lithium. So there's 1 valence electron for lithium. Everybody making sense there? So if we wanted to pick something that's got a valence shell, outer shell, way out here, we would have to get to 2, 10, we'd have to be way down towards the bottom of our periodic table. And there will still be valence electrons. Valence electrons just means what electrons in that element or that molecule are on the very farthest outside. So, if there are valence electrons that are not totally filling the shells, those elements or those compounds, whatever way it is, they will conduct electricity well. Because basically, if I were to take your cup picture and give everybody like 20 cups, if all their cups were full in that outer shell, the valence shell, it gets kind of hard to move electrons between people. But if there's holes in their valence shell, it makes it easier to be passing electrons and sharing them. Because the tricky thing with an electron is, we like to draw them like they're going around this little one atom, but the reality is, in our materials especially that are conductors, that have room in that valence shell, an electron might be going around this atom and then that atom, and they're zipping all around, they're shared all over the place. But if you were to take a snapshot photo of it at any given time, that's when we could count and say, okay, that electron is with this atom, and that's when it adds up. But they are zipping all over the place. But the sum total of how many electrons, how many protons are going to, in a snapshot in time, it's going to follow our rules. So, when you see valence electrons or the valence layer, you've got to know that they're talking about that outermost layer. So, I'm going to give it to you in video format, and basically I think the guy's saying the same thing, but from somebody else. It's kind of like parenting. I've been telling my kids stuff for years, and then their youth pastor tells them, and they're like, Dad, did you know? I'm like, I've been telling you for years. So, we'll see if the video does the same thing.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about valence electrons and how you can use the periodic table to illustrate and diagram them. Let's get started. Atoms are made up of neutrons, protons, and electrons. The nucleus of an atom is made up of positive protons and neutrons, and electrons are found surrounding the nucleus in shells. These shells can be numbered either numerically 1, 2, 3, 4, 5, 6, 7, or with the letters K, L, M, N, O, P, and Q. So let me work a couple demonstrations, and these work for the atomic numbers 1 through 18. After this, there are other rules that apply, and it's not as straightforward. So let's get started with the element carbon. So step 1 is you can locate carbon on the periodic table, and you will notice that it is in the row or period number 2. So that tells you that it's going to have 2 shells. Next, you need to figure out the number of electrons that carbon has. Since it has 6 protons and has a neutral charge, it will have 6 electrons. Next, you begin to fill up the shells, starting from the lowest energy shell and working outward. Now, there's a couple rules for filling up the shells. For these examples, you will need to know that shell 1 or K will hold 2, shell 2 or L will hold 8, up to 8, and 3 or M will hold up to 8 also. So you always fill in the lower energy before the outer. So since carbon has 6 electrons, you will put 2 electrons in the first energy shell, and then you will put 4 in the second, and it looks like this. There's another way you can demonstrate called the Lewis dot structure, and that looks like this. And you basically just take the electrons in the outer shell, which are your valence electrons, and then write them around the symbol. And that's what this looks like. Let's work another example. Let's look at sulfur because it kind of has a higher number, 16. Sulfur is in period 3, so I know it's going to have 3 shells. It has 16 electrons because it has 16 protons. I will place 2 in the first shell. Remember, you always fill up the first shell and work out. 2 in the first, 8 in the second, and that leaves 6 left over. And you'll see they are in the outer shell, so you have 6 valence electrons. And then if you do a Lewis dot structure, it looks like this. So there we go, illustrating and using the periodic table for your valence electrons. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
What's their newest video?
I don't even know how old that one is. Alright. So he went into some interesting parts about how it's 2, 8, and beyond 8. You go, we don't need to go that deep, right? So valence is the outside. If the shell's not full, it likes passing electrons around. That's how deep we're going to go. And if you're deeper in chemistry than that, great, but we probably don't have to go that deep for aviation at the moment.
How do you know how many electrons? Is it always the atomic number?
It's so because we're always going to have a neutral charge. Now I got to be careful with always because later in class we're going to talk about what an ion is. An ion is not quite neutral charge, but everything wants to have a neutral charge. It tries to have a neutral charge. So if there's 6 protons, there will be 6 electrons. If there's 24 protons, there will be 24 electrons because it wants to be electrically balanced.
And the atomic number is referring to amount of protons.
Yes.
Okay.
Yep. The top number, the atomic number, is the number of protons. If you take the atomic mass, it's going to be the protons plus the neutrons, which those two are the ones that have weight. Each proton is a 1, each neutron is a 1, and the electrons, which pretty much don't have any weight to them per se. Very, very light.
So why would that not be 2 if each one is?
Well, the first one, because it's a funny element,
Okay.
it only has an atomic mass of 1, so it's actually missing its neutron. It's a proton only. So the one that's a 2 over here has a proton and a neutron. Good questions. All right. All right, so that brings us right up to ion. That's how good of a question you were, thinking right along the PowerPoint. So an ion is a positively charged molecule. And if you're thinking like I'm thinking, and you're like, it helps me to think electrons, not holes case. If you're thinking electrons, if there's an extra electron zipping around the outside, it's actually what they call an anion, or anion. So an anion is negatively charged. It's actually got an extra electron. But because we're conventional folks, we tend to talk ions, which means it's missing an electron. We'll get into that a lot deeper when we talk about transistors and such, but just know that an ion or an anion is either slightly positive charged, it's missing electrons, or slightly negative charged, it has extra electrons. But things don't like to be that way. They're going to try to get to the balanced, I am not charged electrically. Okay, so current. The definition of current is the flow of electrons, and that's huge. That's what we're going to be going over and over and over and over. We'll give it different symbols, we'll give it different names, but current is the flow of electrons. So as electrons are moving through a conductor is just anything that electrons can flow through. We have what we call current. Conductors are anything that lets electrons flow. Insulators do not let electrons flow well. Insulators are like, nah, I'm not going to share my electrons with you. I'm going to hold on to my electrons, you hold on to your electrons, and we're not going to pass stuff around. So copper is a good conductor. It lets electrons flow through it, it shares them with the atoms, And we use copper for wires, because we can pass electricity through. Rubber, glass, ceramic, air, they don't make good conductors because they don't like to share electrons. So we call them an insulator. An insulator says, no, I'm not sharing electrons with you. So if I were to get the cups back out, I'm not going to do it, but we were considering you guys copper. If I was to put somebody that doesn't like to share in between you, it's going to stop our flow because he's going to go, I'm not sharing with my neighbors, and that stops the flow. So that's an insulator. Insulators don't share. They're not nice people. One more slide and then we get a break. You can do it, Timothy Peak. You can do it. I see you. How many atoms in a copper penny? So when we're talking, okay, how many electrons are moving around? I don't even know if I can count that high, but basically, yeah, there's a lot of zeros there, right? And then when we get into an amp tomorrow, 1 amp is what they call 1 coulomb. It's 1 packet of electrons. And that is the flow of 1 coulomb across a point. So in copper, for instance, there's however many atoms, but then each atom has that many electrons in it as well. So the number is staggering, in the billions, and at that point, my mind doesn't even know what that means. So the thing to understand is 1 atom of copper has 1 penny of copper has 1 billion electrons. So there's a lot of electrons in there for sharing back and forth. Our little picture with the suckers, well, I don't have 1 billion suckers. So you start to get the idea of just how many of these little electrons are flying around in a little tiny piece of material. And we'll cover this a little bit more tomorrow, but 1 amp is 1 coulomb, and a coulomb is a packet, if you will. It's a certain number of electrons per second. So 6.28 billion electrons per second is an amp. And you go, whoa, that's a lot of electrons to be reading on my little amp meter. So that's how tiny these things are and how fast they move. All right, let's take a break, do some exercise. Come on back at, let's say shortly after 8:30. 8:32, somewhere in there.
You know, the bottom right corner says ion.
Oh, must be the screen it's on. There you go. Is an ion positive or negative charge? Does it have an extra electron or not enough electrons?
No. Missing one.
Ion was actually missing an electron. It's a positive charge. Go back. Where was that slide? There we go. Ion is positively charged.
Are they describing the same thing or different? The same state?
It's, if you're standing up here with a cup and you're missing your sucker, you are an ion. You're positively charged, you have a hole. Yep. If you had an extra electron, now you're an anion. You're negatively charged because we call this a negative.
I just wish they would have done it right.
You know, it would have made life easier. They would have. It doesn't so much matter, other than passing tests,
Yeah.
because
Same
the
term.
math works the same, the forces work the same,
Yeah.
and we'll get into that later. We're gonna do the hand rules later today. Dean's like, don't teach them, and I'm like, I think they're good. And it's not so much that you gotta have the hand rules absolutely memorized, as much as you have to know when we reverse a magnetic field, the arrow points the other way. Are they enrolled? Okay, that's okay. They don't have any labs, they might have one they can do now anyway, but perfect. Yeah, you know what, I'll turn the fan on, keep multiply by a billion, and it's not just a single row. Right. They're a million wide, and you start going, okay, yeah, but, yeah, it's a little bit more like we're passing. Very similar to a rope, but if you start pulling, we can do the same thing. If we had a really long rope, if I pulled on my end just a little bit, you immediately feel it on your end of the rope, right?
Literally, yeah, that's just, I guess it's a little easier to understand the chemistry aspect in college.
Well, that's what's tricky with teaching something like this, is you can get it at a deeper, or you might even say more true level.
Yeah, but
But you lose everybody.
It's practical.
Yeah, yeah.
We need to be able to do the practical application more importantly.
Yep.
Yeah. I don't know, my chem class in college, I don't even think I understood it a lot. My professor for that, he was so difficult, dude, had such a reputation for being art class. And he would literally, he would stand at the front of the classroom, like before class started, just staring at the clock. And as soon as the second hand hit 11, he would start talking. And he had a whiteboard that was like a 20-foot long whiteboard across the whole front of the room. And he never used a PowerPoint. He wrote everything out. And he would just start writing. He'd start at one end of the whiteboard, go to the end, come back to the beginning, erase like the first quarter of the stuff, keep writing. Like my pen never lifted off the paper at all.
Trying to
the whole
follow
time.
along. Yeah.
And he would go till like 5 minutes after the class was supposed to end. Like, I don't understand if they need this. But I'm gonna go through
Got all
all
these notes.
Yeah.
Yeah.
I barely passed that class.
That's part of my challenge in here, as we get a little later today, when you start talking the laws. You're like, okay, we can take time to give you the guy that found the law, but you lose the flow of what's actually going on. It's like, maybe we'll come back to it later.
Yeah, I mean, as long as you get, this is the coffee concepts, not the.
Yeah. Especially because when you're working on an airplane, you're never gonna go in the logbook. Using Faraday's law.
Yeah.
It's a generator I replaced. Right? Right. You gotta know why the generator works. Yeah. That's pretty much it. When we get into, I'm a little bit concerned with, I think my toughest class for me to teach is gonna be, what they call, it's like a little 6-day, it's like lighting and communications class. And it's basically electronics, and one of the labs is antennas.
Oh, so it's radio waves and stuff like that.
Yeah, but that's another one of those ones where it's like, okay, how deep?
Yeah, that's true. That can be a deep route.
Yeah. Is it a circular antenna? Linear? Yeah, we're just, so
Yeah.
what when I went through, what they ended up having you do, it was, just memorize the antennas kind of by shape. Be like, okay, I got the shape memorized, so I know what one's GPS and which one's, radio.
What year did you go through?
2019, 2020. I had 16 years of like working heating and cooling, so in the same way as aviation uses electricity, and I was a troubleshooter, service guy, so a lot of years using electricity. Yeah. So I enjoy on the level as aircraft mechanics. Like that's the level I really, really enjoy electricity.
Yeah.
But communications is like, oh snap, that's the, whether you call it next level up or you just say it's a different area. I start getting weaker. And then in aviation, usually you get into that and now you're an avionics technician. We don't really teach avionics in there. There's so much there. Most most people that work on avionics, that's what they do. They're not doing rigging, they're not doing sheet metal work, they're the avionics guy. Even with missions, they'll tend to, it's the avionics guy. And if something goes too much south with avionics, people are sending it off. Give me a new box. Pretty rare for somebody to be pretty deep in avionics and also either airframe or power plant. Happens, but it's rare.
Too many things to keep track. Too many things.
Yeah, you know, it's weird because our brains can handle so much. But I think part of with avionics is it's hard enough to get somebody that's good with avionics. So when you find somebody that likes it and enjoys it, they're like, okay, you are the avionics guy. So even with missions, they'll put them at a base or they'll have them travel. Magnets are so hard to do. It just doesn't.
Yeah.
Get them together.
Can't. They don't want to be together.
You do like an iron filings demonstration.
You know, I wanted to. I got some pictures of iron filings. Do we have iron filings? Maybe we could. We've got.
We could definitely make some not quick.
So we've got. You know what we do for the Magnaflux machine?
No, you
I'm trying to think if that would work.
One today.
What time did I say? Maybe at lab. Maybe we'll try it. We'll try at lab time. That, we're gonna teach about that next, but that still baffles me. I'm like, well, why on a line? What's fun that we're gonna go over, I think it's next. So we just did atoms. What did I say we're doing today? Atoms, magnetism.
Oh,
quartz.
yeah, there's the one underneath the.
There's 3 pieces.
Ions?
Atoms, oh, static. Static electricity. Magnetism. Or static electricity is a little bit of a misnomer when you're trying to teach it. All right. I think we're pretty much good. I'm gonna shut out the back door, make sure everybody's around. If you're missing, we're gonna start back up.
I mean, they know all about. They do a lot of training in that stuff.
All right. So we talked about, we're basically doing 3 things today. The atomic structure that we're dealing with electricity, we're pretty much done with that, with the exception of, so you gotta understand, we're passing electrons around, or if you're conventional, which is what we normally do, we're passing the hole around that wants an electron. We call that a positive charge. So we're gonna go into static electricity next. It's a little bit of a, I use the word misnomer, you'd say oxymoron. It just doesn't actually make a whole lot of sense. The word static means at rest, so there's not movement between it. But when we talk about static electricity and we learn about it, in order to get a static electric charge, we have to move something to get it in the first place. So, whenever you hear static electricity, static, what they're trying to say is we don't have electron flow, or we don't have positive flow, hole flow. But at a snapshot in time, or as we're just hanging out, something will get to where it's positively charged or negatively charged. And that's what we're talking about with static electricity. If we use the word dynamic, electricity. Dynamic means there's movement, there's flow going on. Now, just to be clear, electrons are always moving around atoms, so when we say flow going on from atom to atom or from molecule to molecule, from one place in a conductor to the other side of the conductor, that's what they're going to call dynamic electricity. So if you've got electrons that are being passed, being shared, that's dynamic. Where static is they're just kind of in place and we're getting charged up or negative charge. So this picture here, which you guys can't see real great, it shows a little bit of a spark. I don't know if you've ever like scuffed your feet on the floor too much and then had a static electricity spark. Once I show a picture that shows a spark, am I static electricity or dynamic? Dynamic. So I want to kind of point that out to say we're going to be talking about static electricity, but at the point in time that we're actually transferring the electrons or the positive charge, technically we're not actually static electricity anymore. Now we're dynamic electricity. When we're dealing with airplanes, when we're dealing with wires, conductors, generators, all that stuff, we're talking dynamic electricity. It's the flow of electrons through stuff. But in order to understand that, it's good to understand static electricity as well. Materials that are insulators that don't like to pass electrons around, they can still experience and interact with static electricity, and actually they'll often be materials that we can get more static electricity accumulated on because they don't like to pass their electrons around, right? So if you don't like to pass electrons around, but I can pile up a bunch of extra electrons on you, and you're like, I think I'm going to hold on to these extra electrons. So our insulators, things that don't like to pass electrons around, we can actually still do static electricity with it. It's just they like to hold on to them. That's why conductors, stuff like copper and metal, we don't tend to have static electricity on those because if they get a static charge, either a positive or negative charge, they'll just be like, well, pass that on to something else. I don't need to hold on to that stuff. So static is not moving, dynamic is moving, and when we use the word static electricity as a learning group, we're talking about basically making a whole bunch of, I don't even know if ions and anions is the right word, because it's more like if I've got 1 million atoms, I might have a fraction of that are ions or anions, and that's what we're going to be dealing with static electricity. So, I should have brought a balloon in, but I didn't. If we rub a balloon, a rubber balloon on a wool sweater, we will take some of the electrons that are on the wool sweater, and the friction of it, I don't know why this happens. You don't have to know why this happens, but they tell me it happens. The friction of it will take those electrons and it'll move them to the balloon. Obviously, it's not going to move all of them, but we give it that picture just to say there's going to be an excess of electrons that get moved over to the balloon from that friction. And because the balloon is made out of a material that's an insulator, it doesn't want to give them back because when they're touching, it's like, nah, I'll hold on to those for a while. I don't like to share. So you can rub a balloon on a wool sweater, and you can move electrons over to the balloon. And once the electrons are on the balloon, we would call that balloon negatively charged, right? If the electrons are on the balloon, electrons have a negative charge, so the balloon would be negatively charged. The sweater would be positively charged. It's got a lot of holes that it wants electrons to fill. So that's what static electricity at the basic groundwork is. Now, if I have objects that are statically charged, this is just showing an object, not necessarily a proton or a neutron. So if I have an object that's positively charged, it wants its electrons back. And it's going to say, come here, little electrons, I want you back. That's exactly how it sounds. If you were to listen really close to like a balloon, what you'd hear is you'd hear it saying, come here, little electrons, I want you back. And they're going to want to go towards each other. I'm not going to get into the lines we draw because I don't want to confuse you with magnetism, but you can even draw the static field lines. There's such a thing as static electricity field lines. We're not going to get into drawing them. They have it here. If you have two objects that are positively charged, it's the opposite. They both have too many electrons. Sorry, they're both positive. They both have too many holes, not enough electrons, and they're going to be like, I don't like you because we're both lacking. So we're not going to like each other. So there's a thing that you don't have to memorize, I don't think, called pith balls. Pith balls are basically just balls that you can charge with either positive charge, which means missing electrons, or negative charge, and that says charging rod. So if you put a positive charge on one ball, if the other one is just neutral, relative to each other, they're going to have a different static charge, right? If you put positive on both, the balls will say, I don't like each other, and they'll basically push each other away, very, very similar to a magnetic force. If you have one positive and one negative, they're going to try to transfer those electrons back, essentially. They're going to go, come here, I want you back, and they'll go together. That's kind of all the deeper we're going to go with static electricity. It's a whole field of craziness, but you need to know about it because when we start dealing with stuff on aircraft, which we'll show some slides in a bit, like static electricity wicks or some of our control boards, you need to realize that static is we're not necessarily moving electrons at that given time, and it can be very, very high voltages. Very, very high voltages. So this slide is for you to realize the high voltages we're dealing with, because once we're on our aircraft operating systems, we might be a 12-volt aircraft, we might be a 24-volt aircraft, and we're going to talk about volts is the amount of pressure that's trying to push the electrons through the material. Well, static electricity can be crazy high. A few hundred to a few thousand volts is where you'll typically get a shock by dragging your feet. But even at 2,000 to 4,000 volts of static electricity, it's not flowing through you, you won't even feel that. You won't even feel that kind of voltage if it's not traveling with static. 3,000 volts or so, you can start to feel the static jump from one finger to another, your finger to the doorknob. 6,000 volts. Above that is where if you're jumping on a trampoline and you go touch the springs, it's like 6,000 volts. Zap! And that's why it jumps through the air from your finger over to the springs. You can get up to 25,000 volts of static electricity in static. So when you're talking essentially two insulators and or maybe it's two conductors. You're somewhat of a conductor, and the door frame is metal, so that's a conductor. But I might be able to build up static electricity. I don't think these are rubber shoes and it's not wool floor, but I might be able to build it up to 5,000 to 6,000 volts. But because we're not connected with a conductor right now, the electricity is not flowing, so it's static. So if I come over to the door frame, that's funny, just in the illustration my brain was like, I'm going to shock myself. If I come over to the door frame, once it's built up, when I touch the conductors together, zap. What typically is the case is that kind of static electricity, it's very low amperage. And when we start talking about amps, we're talking about, remember, it was billions of electrons. So I don't have near the billions of electrons with static. But the pressure difference between the two can be very high. So I wanted to touch on that kind of at this point when we're talking static electricity, because when you're looking at aircraft, static is formed typically by friction between two dissimilar objects. Well, our aircraft is one type of object, going through the air, another type of object, and the faster it goes, the more static electricity we can build up. So hanging off the back of a lot of our wings, a lot of our structures, we have what we call static wicks. And those are designed to let that static electricity build up, discharge off the aircraft. Because if we have 20,000 volts that's building up and then zap, discharging into the air just when it builds up, that discharge of electricity, we're going to learn, not only creates fields, but the flow of electricity creates magnetic waves, and it really starts messing with our radios and stuff, because our radios operate off magnetic waves. So that transfer can mess with our radios and everything else, where if we just slowly bleed it off at a kind of continual rate, we don't have this discharge that's going to give us a magnetic field that's going to mess with our radio signals and all that kind of stuff.
Why do those discharge static electricity? Is it like, why do you need?
What a great question. Let me give you the next slide. So, static electricity has this unique property in that the negative charge, which is the electrons, right? If you're statically charged, they tend to congregate. That's the word I'm going to use. They group together. They all assemble themselves on the points of an object. So these aren't great pictures, but you notice how this side of the object is pointier than this side of the object? So the electrons, if you will, the negative charge, it's going to go run down towards the point of that object. If we just had a round surface, now real life is 3D, right? So that gets a little bit tricky. So if we had a round sphere, would be maybe a better way to phrase it. Static electricity will be basically uniform through the whole thing. But if we have pointy objects, and if you really wanted to draw this, you draw a lot more at the actual points. The static wants to run to that point and congregate there. And when it gets a chance, either if the voltage gets so high that it can jump off, or if it comes in contact with something else, it'll jump off that point. So that's why we have static wicks, and if you look at a static wick up close, some of them even have like a little metal tip on them that can be as sharp as a razor blade, because they want it extremely pointy, because basically they don't want static congregating, so it gives it a really, really tiny point for all the electrons to run out to that point, and then because we're traveling through the air, basically they fall off the wagon. And they're like, oh, there's too many electrons on this point, and we're going to fall off into the airstream. So that's why we drag them behind the aircraft into the pointy part off the back, is we're accumulating all these electrons essentially off the back, and they all go to that little point because they like points, and then they fall off the wagon off into the air. So that's the second grade version of how it gets off the aircraft.
And they fall off because the amount of volts.
Yeah,
It's
it's,
the pressure, like, it can't handle.
yeah,
certain-
yep. Because if we raise the voltage, the pressure high enough, it'll transfer either into the air or through the air. So yeah,
Because
and the pointier you get, theoretically, the less volts to get it off, because it's kind of like a reverse logic, right? But the pointier it is, the more focused it's going to get on the end of it, which means it's going to get easier. They're running on a room, and if you've ever ridden in the back of a pickup truck, so Samaritan Aviation, can I put this on the video? When we go to the air show, a lot of times there's not room in the pickup after the night show, and I think we've had up to like 16 people in the back of the pickup truck. And then we drive back to our campsite, and we're lucky that somebody doesn't fall off the back of that pickup truck. So, similar kind of idea. They run to the point, and there's just not room, which makes it easier to fall off. Where if we're all spread out evenly over a surface, everybody's got room, and nobody wants to fall off then. So that's the best explanation I can come up with. it's a comparatively, so if it's a very big buildup of the negative, it's a comparison. And that's what we're going to get into tomorrow, is the math of, we're comparing two different objects. So yeah, I can either have a crazy high positive and just something, we'll go with negative, or crazy high negative, just something a little bit less negative. They'll move when there's a difference between them. It's not just one has to be positive, one has to be negative, it's a difference between two. Okay, I've got a video for you again, so we're doing kind of the same thing. I described static electricity to you. We're going to do a video, and that was a really short session, which means I'm cranking through. But we'll do a video and then another little break. We'll see how this guy does with static electricity. But it's not always static, because once it starts moving, it's dynamic. Oh, all these funny rules. Where'd it go?
Have you ever had your hair stand on end after combing it, or after you've rubbed a rubber balloon against it? This video will look at the physics behind static electricity. It might help you if you first viewed the video on atomic structure.
We learned about it.
Current electricity is a relatively recent discovery, whereas the effects of static electricity were written about over 2,000 years ago in ancient Greece. As the name static electricity suggests, it is static, it doesn't move. Metals allow the flow of electrons in current electricity, but here we are dealing with all the other materials that are not metals and are insulators. If two different non-metal insulators, a cloth and a glass rod for example, rub against each other, then both may become charged by friction. As they rub together, electrons may be removed from the surface of one and deposited on the surface of the other. Once there, the electrons cannot move, they are static. Since all materials are naturally electrically neutral because they have an equal number of protons to electrons, this transfer of electrons leaves one material with less electrons and less negative charge than it had before, and the other material has more electrons. So one of the materials becomes positively charged and the other is negatively charged. This can be seen when a plastic rod, such as a ruler, is rubbed with a soft cloth. Electrons may be transferred from the cloth to the ruler. If two identical rulers are charged in this way, and one is suspended in a simple cradle as shown, as the end of one ruler is brought closer to the other, repulsion is seen as the suspended ruler turns. It is pushed away. Holding the cloth used for charging near to the ruler will attract it toward the cloth. This shows that there are two types of charge, positive and negative. So alike charges repel or push each other away, whereas opposite charges attract each other or move towards each other. Which material becomes positive or negative depends on the identity of each. This happens when you brush your hair. The brush and the hair take on opposite charges and so become attracted to each other. There may even be a crackle, and in a darkened room you may see tiny sparks as the electrons jump the small gap to make the materials electrically neutral once more. This often happens when removing clothing made of certain fabrics. This is a party trick where a rubber balloon, after rubbing against a cloth or a jumper, or even someone's hair, can be made to stick to a wall. This works as the charge given to the balloon, let's say is positive, when brought near to the wall causes or induces a slight charge separation in the wall as negative charge is attracted towards the surface. This induced slight negative charge is sufficient to attract and hold on to the positively charged balloon, so it sticks.
I just want to stop and point out, remember he said we're talking about insulators, so the reason the charges don't balance between the wall and the balloon is those materials, they don't like to share. So even though they want to share and they're being attracted to each other, the electrons, they don't like to move. We had to do a lot of work to make them move. So just pointing out and reminding you, that's why static is typically found in insulators, is we can get them charged, but they don't like to share.
Even holding a freshly charged plastic comb next to a thin stream of water from a tap shows a similar effect, that of induced attraction. The slight spark caused by the electrons jumping from one material to another can be dangerous. Petrol and other liquid fuels build up a static charge as they flow through a plastic pipeline. There is an earthing cable connected to the fuel nozzle at a garage, and aeroplanes are linked via a similar cable during fueling to prevent a static spark igniting the fuel and causing an explosion. So the next time you drag your rubber shoes across a carpet and then touch a door handle or your friend, and you hear a click and feel a small shock, you know that you have just witnessed static electricity in action.
So that is my, I'm going to call it attempt to touch on static electricity, because we deal with it in aviation. We deal with it especially as we get into circuit boards and controls. You'll end up seeing bags like this that stuff comes in, and the idea behind a bag like that is it's supposed to not allow static electricity to jump through or transfer. So they'll call it an anti-static or a static shielding bag. Is if you put this inside there, we shouldn't be able to transfer electrons through the bag. So it's basically a really good, not only insulator, but also it blocks a static charge. Because I would not want to drag my feet across the ground and get all electrically charged up and then grab onto a circuit board like this. Because if I'm at 25,000 volts or even 6,000 volts, and I start touching the terminals at 6,000 volts, well, some of these components, maybe not this one, but components and transistors, if they see 6,000 volts across them, they're going to go, I give up, I'm done. And you can actually burn them up with static electricity and cause some pretty major problems. So that's why we took 15-20 minutes to touch on static. It's so you know what's going on. It's a very high voltage, but a very low current. But it'll come back on stuff like protective bag. If you take a radio out of an aircraft, they'll want you often to plug the ends of it. It's not just for dirt, but it's so during handling and walking around, and when we pick up 6,000 volts of static electricity, we don't accidentally send 6,000 volts through some really tiny components that can't handle 6,000 volts. So after we come back from static, we will go into magnetism, which is really the important part of electricity and how we make it and how it's going to work. So I'm going to take a break as well. Why don't we come back? Let's make this a long one and make it 9:10. We'll come back at 9:10. I haven't seen, I was going to bring my spike ball in. Should make a note. Yeah.
So, on like your demonstration of like a balloon rubbing on air, is an electron moving to the balloon always negative or always positive, or is it
Electrons are always
or not,
negative.
Not electron, but whatever's moving through the balloon, is that negative or positive?
Yeah, so electrons are always negative charged. So if the electrons move to the balloon would be negatively charged.
Okay.
And whatever the electrons left, now they have a hole in them, and we call that positively charged.
So can you tell like which one it is?
Yep. If you have a,
So like is
well,
the balloon-
static gets tricky because it's static, but your voltmeter will either give you a plus or a minus. That's a good question. Once we get into, I'm going to call it not static electricity, because really dynamic electricity, what we use, all it is static electricity, but it's established. Instead of one little spark, we have a continuous flow, so we call it dynamic. So, your voltmeter, when you touch a probe, red probe, black probe, if it's hooked up correctly, if I were to touch the red one on the positive and the black one on the negative, it'll show that voltage. If it turns out that it was reversed, it'll show me a negative number. So, yeah. So these will read positive and negative charge.
So when you have positive charges left, because you've taken out the electrons,
Yep.
you then, you call that a positive charge, but is that then more protons versus electrons?
Correct.
But because we're dealing with electricity, we don't call them protons, we just
Exactly.
refer to the electrical.
Yeah, because protons don't move. Protons stay in their element. It's the electrons that move. So that's back to, and we'll cover that, it's actually tomorrow. And we're touching on it now. When we say conventional flow, we imagine essentially the protons moving. But that's how everything is drawn with conventional flow, where in reality, it's actually reverse of that. Stuff's actually moving the other direction. It's electron flow. And it works the same, the math's the same, everything is the same. You just gotta make sure when you're talking about it, you go, hold on, are we talking electron flow, or are we talking conventional flow here? Still works the same, it's just which verbiage are you using? So a battery, the positive terminal of your battery has a positive charge, it's lacking electrons. The negative terminal has extra electrons, so it's a negative charge. But when you hook a battery up to something, you normally think of power going from the positive to the negative, right? And that's how we talk about it. But in reality, electrons are going from the negative to the positive terminal. So you gotta make sure, okay, what are we talking here? There's kind of two ways to teach this. One is to not even introduce electron flow, so we don't confuse people. The other one is to go over it a lot like we are, so that you guys are like, okay, I get both. So if you don't talk about it at all, what happens is pictures in your book will list it in the reverse. They'll list electron flow once, and you'll be like, wait, I thought I understood this. This has it backwards. And we're gonna cover that. The rule in aviation is unless stated otherwise, we always speak in conventional. And then some people break rules.